All right, so in the last lecture, I told you a few things about how to parallelize things on a single machine. So let's say my laptop here has 8 cores. It has 16 gigabytes of memory, which in a few years probably is going to be very small. But when we want to use this, there's a methodology to program on computers where you have one global object in memory on this machine, and this memory is accessible to all of the processors of this machine. And then what you would want to do is you would describe the operations you have in such a way that they can operate in parallel on the different cores of my computer, but they all access the same memory. The alternative, of course, is that if you have multiple machines, they all have their own case and their own processors and their own memory, but they cannot access each other's memory. And that leads to a programming paradigm that we call parallel distributed, which typically is programmed with a set of functions, or let's say a model that we call the message passing interface, MPI. So what I'm going to tell you about in this lecture is an introduction into MPI. MPI, as I said, is the message passing interface. It is a set of functions that I'm going to introduce you, and let's say what I'm going to talk more about is the mindset behind that. So in the previous lecture, what we talked about was how you program, how you think about parallelization in the context of a single address space. So a single address space means you have memory that is accessible from all processing units, from all processors or all cores or all threads of your program. So in that case, all of them have access to the same data. That makes parallelization a lot simpler. You never have to ask the question, well, where's my data? How do I get the data that I need to do a particular computation from? The disadvantages of this, of course, the problem size is limited by the size of the machine, right? If I have only 8 cores in this machine, then let's say I cannot split up my job into more than 8 different tasks or threads. Or if I did, I can certainly not expect it to be faster than 8 times faster than what we experience if we run the same program on a single core. Similarly, if I have a machine that has X amount of memory, then that's it, right? If my problem does not fit into there, I cannot expect to solve bigger problems, because my assumption in this shared memory programming model was that every thread of execution, every task, every thread, every process has access to all of the memory. So if I have exhausted the 16 gigabytes of my laptop, that's it. Bigger problems are simply not possible. And then there's a particular problem that we have hit in the last few years. Since about 2005, processors have not become faster in terms of clock speed. They can do a few more operations per clock tick, but the limit is typically how much data you can get from memory onto the processor. Now, if I have one processor, like in this laptop, which has 8 cores, then that means that 8 cores want to get data from memory onto the chip. And that creates a bottleneck. Today, memory is the slowest part of a computer. So the more cores I get, the more this memory bandwidth becomes the bottleneck. The only way I can address this, of course, is if I take multiple machines with multiple processors and their own memory. So that's one of the disadvantages of shared memory programming. Other things that don't work so well with shared memory is that I need to synchronize via locks. So I've shown you how to do this with a data structure that's called a mutex, a mutual exclusion object. And finally, one of the things that we found is that it is just way too easy to avoid hard decisions when you program with threads. When you program with threads, you can assume that all of the data you need is locally available. But oftentimes what you find is that if you run multiple threads operating on the same data structure, they all update the same data structure, and they need to exclude each other with a mutex, for example. So I've shown you how to do this with a matrix. Now imagine, for example, you have, let's say, 64 or 512 cores in a few years on a processor, and all of them try to write into the same matrix. If they exclude each other from writing into the matrix with a mutex, you will find that they almost all spend all of the time being excluded from the zone where they write into the mutex, because 512 processors, of course, all want to write into the matrix at the same time, and only a very small fraction of the time is actually spent on computing matrix entries. So what you find in this context then is that one approach would be that, let's say, you don't keep just one global matrix, but you would have one matrix object for every thread. That's possible with multiple threads, and we sometimes do this, but it's a difficult decision to make because it incredibly complicates the programming model we have. Now, what I want to say with this is that when you program with shared memory threads, for example, it is too easy to make the easy decisions, and it is painful to make the hard decisions, and as a consequence, almost all the time we end up with programs that actually don't scale so well. So to give you an example, to just repeat what we did in the last lecture, is when you do shared memory, that means that there is one global triangulation object, one DOF handler, one matrix, one right-hand side vector, just one object that lives in memory. Multiple threads all work on this one object of each kind. So for example, multiple threads help to assemble a linear system. They all work on different cells, but they all write into the same entries of the matrix. They perform matrix vector products on the same matrix in the same vector. They estimate the error per cell. They generate graphical output, and so on and so forth. Point being, all threads access the same global object, and there are multiple tutorial programs that show this, as well as a documentation module, very extensive one, that talks about parallel computing with multiple processors using shared memory. What I'm going to talk about in this lecture here is the opposite view, where you have multiple machines, and they all have their own memory space, and work under local copies of data that may be just portions of what makes up a matrix, or portions of what makes up the triangulation. So they have their own address space. In particular, they have no direct access to remote data. So if you, let's say, split a triangulation onto 1,000 processors, that means each processor has a certain share of the domain. Now, that means that if processor 1, who has the part of the domain over here, and processor 2 has its part over here, if processor 1 wants to know something about processor 2, it can't just go read the memory that corresponds to this piece of information, because it's not locally available. It sits on the memory chips of another computer. They're connected by an interconnect, but you can't access that memory over here. So the only way around this is that you transport data explicitly between machines. So that means if processor 1 needs something, it needs to ask processor 2 for it, and processor 2 needs to send the data back. The advantage is that you can use an almost unlimited number of cores in memory. Today, the biggest machines have on the order of 1 million processors, and each one of these has maybe 2 gigabytes, so you end up with petabytes of memory. We can use these machines with this model, with this programming model. In practice, this often scales better than shared memory because we are forced to make the hard decisions that require us to split data structures, to split algorithms in a way that can scale. Things that we could in principle do with shared memory programming, but in practice almost always not do. The disadvantages of this is that it's a much more complicated programming model. You actually have to think very different about where data resides, how you transfer data from one machine to another machine, and so on and so forth. So in particular, it's not just that it's complicated technically, but it requires a completely different way of thinking about problems. And I'm going to introduce a few examples to you later that show how we think about these sort of things. In practice, there are difficulties that are associated with debugging and profiling. It turns out that it's just difficult, and I'm going to show you a few examples where I demonstrate how to debug programs as well in MPI, and you will understand why I say that it's difficult. So, as an example, if you went with this distributed memory programming model, you would essentially have something that conceptually is one triangulation, so a collection of cells that live on all of the processors, but that means that every processor has its own, in its own memory space, has its own triangulation object, has its own DOF handler object, has its own matrix and right-hand side object, and they all give you a piece of the information that, if you take it together between all of the processors, describes, for example, the triangulation of the entire domain. So the union of each one of these objects, the union of the triangulations on processor 1, 2, 3 to n, the union of all of these objects describes a global object. Multiple programs work in parallel. So when I say multiple programs, that means the programs that run on each one of these processors, they all work together to assemble this matrix. Now, each one of them assembles the part of the matrix that corresponds to the cells that this particular processor owns. Okay. Similarly, when you do a matrix vector product, each one of the processors does a matrix vector product with its own part of the matrix and its own part of the vector. Same for estimating the error, same for generating graphical output, where again every processor is going to be responsible to create a file or a piece of a file that corresponds to the cells that live on that particular processor. Like I said, the general model that's behind this is that each program can only access the part of the global object that is stored locally. Now, the canonical examples in the deal.II tutorial are step 40, and then bigger ones are 32 and 42. I'm going to show you step 40 in the lecture after the next, where we're going to look at how is it actually implemented, and I'm going to show you how to run it and how to visualize data. All right, so more technically, when you want to go the route of distributed memory computing, so you want to use multiple machines that all work together with their own memory spaces to solve problems, there are a number of different approaches or a number of different programming methodologies for this. One is called MPI, the message passing interface, which is by far the most widely used in scientific computing. You could also go along a route that is called remote procedure calls. Essentially what that means is that one processor can call a function on a different machine, which might fetch some memory and then return it. That is something that we don't use very often in scientific computing because it is more suited to, let's say, database lookup. Let's say you would have a distributed database that's so large that it doesn't fit into the memory of one machine. You would, if you wanted to look up something in the database that is stored somewhere else, you would just call a procedure, a function on that other machine, which looks up the information and returns it. Like I said, we don't use that very much. It's not so well suited to scientific computing. There is a number of different languages, so other than C, C++, and Fortran, that address specific problems that we see in scientific computing. And the names for this they run under the heading partitioned global address space. So essentially what that means is that we pretend that every processor has access to all of the memory on its own machine and all of the other machines. So there's a global address space, but it is partitioned into the piece that we own locally and the pieces that are located on other processors' memory. So the languages that do this are called, for example, Unified Parallel C, UPC, which is an extension of C. There's Co-Array Fortran, which is a part of the Fortran 2008 standard. And then there's completely different languages that are called Chapel, X11, and Titanium, for example, that do these sort of things. I'm not a big fan of these languages, and I think they haven't really caught on in scientific computing because they pretend that you can access memory from other machines when in reality that's not really true. I mean, the language allows you to access memory that is stored on other machines, but it's incredibly slow, right? You would have to go through a network card, through the network, go to some other machine, look the data up there, send it back. So even though the language pretends that you have access to this memory, in practice it is very slow. And you run into the same problems that I just outlined for shared memory programming, that it just makes it so easy to write programs. I mean, it's it looks like it's trivial to access all of these global objects, and it is trivial, but it's inefficient. So what we find is that we can write programs in these languages very easily with very little code, but they don't scale. And I mean, if we are interested in running things on, let's say, 1,000 cores or 10,000 cores, then it matters a great deal whether it scales or not, right? So it's this trade-off between being easy and being efficient. And I think what we find in distributed memory computing is that we need to err on the side of efficient, because if we lose efficiency, we very quickly are at only, let's say, 1% efficiency. Well, you throw 1,000 processors at it, and it runs only 10 times faster. That's not worth it, right? Okay, so I will talk exclusively about MPI, the message passing interface, and so let me introduce you a few terms. So in MPI, we have something that we might call a universe. It consists of processes. So the universe is something like the collection of all of the machines that participate in a particular computation, and on each machine, or each core of each machine, we have one MPI process running. So a process is essentially an executable that is running, right? And we tie that to one particular memory space. Most of the time, we run processes in a way where we have one single-threaded process per core. So let's say if I couple together 4 machines, each of which have 64 cores, then the way I would do this is that on each one of these machines, I would run 64 MPI processes for a total of 4 times 64 equals 256 processes. Each one of these processes is tied to one particular core of these machines. So it doesn't really make sense to run multiple threads on each of these processes, because I already have 64 processes running on 64 cores on every machine. Now, if these processes were multi-threaded, which I can do using the techniques that we talked about in the last lecture, then I could, for example, on every machine run only 16 processes, each of which uses 4 threads. That's possible. We call this hybrid parallelization. It's not very common to do it, but it's possible. So within this universe, like I say, every process lives on its own machine or on its own core. It has its own memory. And if you want to access memory from some other process, or if you want to send information to some other process, we do this by sending messages. Now, the mental model of sending messages is essentially like a mail system, like the US postal system. So I would write a letter on which I put the information that I want to send to somebody else, and I would put it in a mail system, and the mail carrier comes and picks it up and delivers it to some other person's mailbox. And at that other person's mailbox, the person can go there, can find the letter, can unpack it. Maybe it contains instructions of what I want. Then the person would follow these instructions, would look up some piece of information, and would send it back to me through the mail service. The analogy is pretty good because it already highlights the problems that there are. So for example, if I send a letter, but the person who I send it to does not ever pick up the letter, then nothing is going to happen. So if I wait for a return mail that contains the information that I needed from that other person, but if that other person never picked up the letter with the instruction, or if the other person picked up the instructions but never put a return mail into the mail, then I will wait forever, right? I will stand in front of my mailbox and wait for that mail truck, and the mail truck does not come. So you can really think of these messages that we send as messages that go through a mail service, and the mail service is going to put things into the mailbox. It's not going to actually deliver it to the person and say, here, read. But the reading has to happen actively. The mail might be in the mailbox, but if nobody comes and reads it, then nothing is going to happen. That leads to situations that we call deadlocks, and I'm going to show you the consequences of this in the next lecture. So in the MPI model, I cannot just access data that lives on some other process or in the memory space of some other process, but I have 2 options. The first one is if I need information from somewhere else, I can send a request message to somebody else. The other side has to pick it up, has to know what to do with that message, so it needs to be able to read my instructions, for example, has to put the data that I wanted into a message that it sends itself, and then the whole thing goes back to me and I have to pick it up. That's in practice a relatively inefficient process. So in practice, oftentimes what we do is we follow option number 2. So option number 2 is essentially, if I know where in the process of computing something I am, and if processors do more or less the same work everywhere on all of the machines that we have, then typically I also know where that other process is. So I can anticipate, for example, that the other process is going to need some piece of information that I have in the near future, and I can send that. So I don't need to wait for a request to come in. I might as well send the data that I know the other processor is going to need, and I do that on my own, and the other process then just needs to find the mail whenever it's time for it. I'll show you this second option in a minute when we talk about matrix vector products, because matrix vector products are relatively easy to understand, and there's a point in the algorithm where in order to do my local work I need to know what the other processors have in terms of data for the vector they store. So the other processor, knowing that I'm going to need it, is going to send it to me right away. I don't need to send a request if the other person already knows that I need it. Okay, so in practice, this model where we send messages is a little bit bothersome. I think that's certainly true. It's more difficult to send messages and just walk into somebody else's house and get the data. But in practice, what that means is that it exposes the programmer of a program to what would happen anyway in any other scenario that you could think of in terms of parallel programming. If processes have different memory spaces where you cannot read what the other process has, at one point you will have to communicate. And the great strengths, for all of its weaknesses, the great strengths of MPI is that it makes this model explicit, that you have to think about what is happening, that you have to think about how to do it efficiently, and that is typically the step that makes it possible to write efficient programs, that you have to think about it. One of the things that you can do to make it, amortize the effort that you have to put in is that you don't actually have to send messages and wait for the next thing to come, but you can interleave this. For example, when I show you how to do matrix vector products, I will show you how we send the data right at the beginning, and then we do something in the middle, and then we wait for data to come in. Well, that data might actually have come while we were doing something in between, right? So we can interleave sending and receiving and computation in such a way that we don't have to actually wait for something to come in, but we do something productive in the meantime. In practice, like I said, this process has been shown to scale to well over 1 million processes, and by the time you watch this lecture, probably many more than this. Okay, so how does MPI work? MPI is not a programming language. It is essentially just a set of functions, data types, and constants that you can access from C and Fortran programs. That's what's in the standard. And of course, if this is possible in C, then it is possible in C++, because C++ is compatible with C in most ways. It is not a language of its own. It can be compiled by any standard C and Fortran compiler. Typically, what happens is that every MPI implementation, of which there are many, every MPI implementation has a program that is called, for example, MPI-CC, so the MPI-C compiler. And then you would just compile your program myproc.c into myproc.o like you always do for every object files. The same thing if you wanted to run C++ programs, then you would call MPI capital CC, or if you wanted to compile Fortran 90 programs, you would call MPI F90. These are not compilers, these are just wrappers. Essentially what they do is they call the compiler that you have on your system with a specific set of flags. For example, link with this library, and here's the path to the header files that we need for MPI. Many other languages have bindings, so you can call MPI from C and from Fortran, of course, because that's what the standard says, but there are bindings for Perl, for Python, for practically any other language that you can think of. They may not be officially supported by the MPI standard, but it's possible to use MPI in many other programming languages as well. So the MPI implementation, how it really works, is all based on messages. Namely, you would send messages from one processor to the other. And that's the bottommost layer of MPI, and everything else builds on this. So you can send messages from one processor to another, and you can see if there's, basically there's three operations. You can send a message to somebody else. You can check your mailbox and see if there's a message. And if there's a message, then you can receive it. And if you just ask to receive it, but there's nothing, then you wait until something comes in. So here's an example. Let's say I'm on process number 2, and I want to send something to process number 13. So let's say I have computed with a function called foo a variable d, that's, let's say, a double precision data type. And let's say I want to send this to process number 13. Then I would call this function MPI send. And so you see this is pretty low level, right? MPI send asks or requires the following information. So it wants a pointer to the data, so the address of D, okay? Then it wants to know how many elements of this data are there. Well, I want to send only one double, so the count is 1. What's the type of the data that should be transmitted? That, in my case, is a double. So there's a constant that is called MPI_double for the type. Who do I want to send it to? That's process number 13. Then I can put a tag on every message. So a tag is something like an identifier what this message is supposed to indicate. I don't know what it should be here. Let me choose 42, for example. And then the last argument of any MPI call is what we call a communicator. So a communicator is something like the mail service that I want to use. So MPI com_world would be the mail service that connects all of the machines that participate in the computation. It's the universe. I can subset this. So what I should say is that the destination 13 is, let's say, something like a house number within the universe in which I work. I can create, let's say, smaller mail services. Let's say, for example, something that only pertains to all of the processors that work along the left edge of my domain. Then in that case, I would create a universe that has only a subset of these processes. And if I say then destination 13, that would be the 13th participant in this smaller universe. Okay. Okay, so here's an example how you would query for the data. So that's the second kind of operation. So querying would work with a function call that is called MPI iProbe. So I want to know, did some mail come in from process 13? So I would say, okay, I probe for messages from processor 13 with tag number 42. Then it's going to return an integer that is, in this case, either 1 or 0 that says, is there a message or is there not? I need to say which universe I work on, and then there's a status object that I can query that has some additional information. If I just care about the fact, was there any mail at all, I can replace the 13 here by a special source that would say anywhere. I must admit I forgot what the exact name in MPI is, but there is a constant that would identify, is there something from anybody? And there is a special constant for the tag that would say, is there something from somebody with any tag? Let's say if I don't care what the tag is, if I just want to know, is there something? The third kind of operation was how to receive a message. So when you want to receive a message, that assumes that something is already there. And in that case, I would call a function that is called MPI receive. And again, I need to say, where should the data be? So that's a pointer to some memory space. In this case, it is a pointer to a double variable. How many of these do I expect with the data type? In this case, double. I expected from processor 2, which is the processor that just sent me something, I expected with tag number 42 in this universe, and that's the status object again. And again, if I want to receive messages from anywhere or with any tag, I can specify something different for the 2 and the 42 here. One of the things that's important to understand is that if there is no mail, if I have not gotten anything from processor 2 with tag 42, then this function will hang as long as it takes until that message comes. So if that message never comes, my job will sit idle, doing nothing. And that's what we call a deadlock. So I'll show you situations like this later on. That's one of the things that are really difficult to debug, well, comparatively difficult, because you don't quite understand where your program is. You need to understand not just where is the program, why does it, so you will easily see in a debugger that you're an MPI receive, but the question is why am I there? Well, I'm there not because this particular process did something wrong, but for example, because some other process did not send a message. So the cause for an error is not something that you can find out only by looking at where you are, but you actually need to understand what the other processes have been doing. Okay, so a few notes. When you say MPI send, then what happens is that the program blocks. Blocking is a term that is defined by MPI. Essentially, that means that the MPI implementation will only return from calling MPI send once the data is actually out of the door. That means it has been copied out of your own memory space to wherever it needs to be. It doesn't have to have crossed the wire already to the other machine, but at least once it returns, you can safely delete the data in the next statement if you want to, and MPI will not have to access it anymore. Similarly, if you call MPI receive, the program blocks until there is a message that comes in and the data has been copied into the final location that was given as the pointer in the first argument of MPI receive. These are things that are, in practice, maybe a little bit restrictive. For example, you could say maybe I want the MPI sent to immediate, so it should register that I want to copy this particular data from here to some other machine, but it should immediately return, and when that copying actually happens, that is something that I don't care about. Maybe that data will always stay there in this piece of memory, and MPI should just send it when network capacity is available. So if you wanted to do this, there is a function called that does that is called MPI iSend. And similarly, there is an MPI iReceive. So MPI iReceive would, for example, wait. I mean, it registers that you want data to be copied into a particular location, but it immediately returns and allows you to do other things. And when that data finally receives, MPI in the background will copy it into the location that you wanted. Now, for both of these things, you need to have a way to figure out if data has been sent or if it had been received and put into the memory location, so that once you actually need it, you can say, okay, I want to wait for this operation to really finish, and there's a call for that is called MPI wait. So that allows you to interleave actually sending and receiving data with doing computations. Okay, on top of these message passing approaches, there are you can build higher layers. So the next higher level on MPI would be called collective operations. So collective operations would be something that you can build on sending messages, but for which there are specialized functions in MPI that allow you to do this. For example, one of these operations is called barrier. And a barrier I always compare with a track and field event, let's say the 100-meter sprint. Essentially what the referee says, it asks all of the participants, are you ready? And only when they all have responded, yes, I'm ready, then the gun is triggered and you can start running. And that means that all of these participants can only start doing this once really every participant has arrived, right? It's not like you say, okay, well, whenever you arrive, just go, right? So barrier really waits until all of the participants are there, and once they all have said that they're here, then they can all go. So that is something that we don't use very often in our algorithms, but that's very useful, for example, when we do timing. So if I want to figure out how long does this particular operation take, I don't want everybody else to start whenever they're ready and then to hang somewhere in the operation because processor number 42 has not arrived yet and hasn't started working on this, and as a consequence hasn't sent pieces of data that other processors needed. So barriers are something that you often use for debugging to figure out or to ensure that every process in your program is at exactly the same location. Other operations that you can use are broadcast, for example. Broadcast would mean that I am sending the same piece of data to everybody. So let's say it's a flyer that I send to everybody. For example, okay, I have finished this particular computation with this result. Here, now you all go. So a typical application would be, let's say, if everybody has to work, let's say I get a new picture from a telescope. And I'm going to send that to 50 different processors that do different manipulations on it. So in that case, I would broadcast that picture to all of the processors, and they all go off and do whatever they need to do with it. In addition to broadcast, there's an operation that is called scatter. So scatter would mean that I have, let's say, 50 pieces of data, and I scatter that to 50 processors, and each one gets exactly one piece of that. It's an operation we don't do very often. The opposite would be gather, where, let's say, all of these 50 processors have computed something, and I want to get that all onto one processor. That's a gather operation. So I will get all 50 pieces of information into one big array of size 50. Or that all processors have computed something, and now they all need to know about it. That would be an all gather. So at the end of an all gather operation, every processor has all 50 pieces of data. And then there are operations that we call reduce and all reduce. So in that case, so in a gather, you get 50 copies of, or 50 pieces of data on every processor. Let's say you want to add them all together. That is a reduce operation. So you want to take, let's say, the sum of what every processor has computed. Reduce does this on one processor, and if you did all reduce, every processor gets the result. So these collective operations, let's say an all reduce or an all gather, can in principle be implemented by having a reduce where you compute the result on one processor, and then you do a broadcast and you send it to all. So an all reduce is something like reduce plus broadcast. An all gather would be a gather plus a broadcast. Okay. One of the things that is important to realize is that in these collective operations where everybody participates, if somebody does not participate, then all of the processes hang, right? If I'm asking for everybody to please send me your data, and everybody but process 42 does, then everybody waits, right? If I can only continue once every single process has sent me the data. That's again what we call a deadlock, where one processor is waiting for something, but the other processor is not sending it to me. Okay, so here's a few examples, practical examples. So if I show you, I talked about the barrier that MPI implements. So here's an example of a barrier. If I do this in C++, for example, let's say I have a function that I call foo, and I want to figure out how long does this function run. Then one of the ways I can do this is that I use this data type standard : time point, okay, and I'm going to initialize it with std now. So it saves the current time, and then I run this function, and at the end I'm going to ask for now again, okay. So if I take the difference between start and end local, so start and end local, that gives me the amount of time that it took this particular function foo to run. Okay. Now, it may be that this function is very quick on one processor, but not on the other. So let's say it took me 1 second to run this on processor 1, but it takes 10 seconds to run on processor 2. And if I wanted to output how long this function runs, then what I probably care about is, let's say, what did it take the slowest processor to do this? So in order to do this, it doesn't help me if I, let's say, on one particular processor call or take the difference between end local and start. But what I need to do is I need to take the difference between the start time and the time when the last one has finished. Okay, and how do I find out when the last one has finished? Well, that's how I use this barrier. So if I'm on processor 1 and it is fast, I immediately hit this. Let's say I do something for a second here, and I hit this MPI barrier. And in this MPI barrier, I'm going to be stuck until the last processor checks in and says, yes, I'm here. Okay, and then they can all run again. That's when the gun is triggered and we can all run. So on processor 1, even though this took only 1 second here, I'm going to wait in this MPI barrier until the last processor has finished calling or running foo, and then I take now. Okay, so the difference between end global and start is going to be the global amount of time that this foo takes, the maximum of all of the processors. And you will easily see why it is also important to call the barrier up front here immediately before calling or before determining the start time, because what matters is not just when this process starts, but I need to make sure that all of these processes start at exactly the same time. Otherwise, it could be that processor 2 still has something else to do before it even gets to foo. So I already start. It takes a second. Processor 2 hasn't even started yet, but my end time starts running already, right? So I need, whenever I do timing in parallel, I almost always need a barrier immediately before calling STD now. Here's an example of a reduction operation. So let's say I have a parallel distributed triangulation. That's an object you will get to see in step 40. Essentially what that is every process has its own piece of the triangulation, and across an MPI universe we have the entire domain mapped out. So I can ask this triangulation about the number of cells it owns locally. So if I want to know the global number of cells, then I need to add this up over all processors, right? So I'm asking the number of my cells, and I'm going to put this into an MPI reduce call, where I'm going to say I want the address of my cells. That's the piece of memory that we should have a reduction operation on. I want the result to be put into global cells. The data type is an unsigned int. I have only one element that I want to have the reduction done over. The operation is a sum operation. I want the result to be at processor 0, and I want it in the universe MPI world. So in this example, MPI reduce only computes the result at root number 0, so on processor number 0. All of the other processors call this function, but they will not get the result. If they wanted the result, I needed to compute MPI, or needed to call MPI all reduce. The way this is implemented is that, in principle, you could implement it in a way where every processor just sends its own myCells variable to processor 0, and on processor 0 you just add it all up. That turns out to be not very effective, because you would end up with a lot of data all being sent to one particular processor. And so what happens is, for example, let's say I have 4 processors. Then processor 1 would send it to 0. Processor 4 would send it to 3, and processor 3 would send it to 0. So you have something like, for example, a binary tree where the root is the place where you want it. So if 4 sends it to 3, 3 adds it to its own number, and then 3 sends it to 0, which adds it to its own number. You can easily verify that that requires a log n, where n is the number of processors, log n messages being sent, but you avoid the bottleneck that everybody tries to send to one processor. And it doesn't have to be a binary tree. It could also be that, let's say, a ternary tree, or a tree with 4 leaves for each node. But you get the idea that we can do this in a hierarchic sense. Okay. Yes, if you wanted it at every processor, you can call all reduce, and all reduce is the same as an MPI reduce plus a broadcast. Okay, so higher layers. If you build on top of these collective operations, you can go beyond this. For example, MPI world is the universe of all of the processes that participate in a computation, but you can take subsets of these. Okay, we call these also we call these communicators. So the MPI comworld is the universal communicator, but I can take subsets of these. And the ranks that I add, let's say the rank is the number of a process within each communicator. That's something that we don't do very often, but it is possible. Let's say you have a model where you run both an atmospheric and an ocean model. They need to communicate with each other, of course, but in every time step you first, let's say, want to compute something for the ocean, and then you would have a communicator that only couples all of those processors that do something with the ocean. And at the same time, for example, you would have another communicator that couples all of those processes that deal with the atmosphere. So they can communicate between each other to compute a solution of a time step. And at the end of this, you would have information that is exchanged between all of the ones on the ocean and all of the ones on the atmospheric side. So they would use MPI comworld to exchange this information, and then they go off and do work again on their own communicator. Okay, other things that you can do with MPI, there's an I/O layer. You can easily imagine that if you have 1,000 machines or 10,000 or 100,000 and they all try to write to the file system at the same time, that you get into trouble. So MPI provides ways to make this more efficient. There are functions that do this. I don't want to go into too much detail, but MPI has this sort of stuff. It also has something that is called one-sided communication, which is essentially I can read and write into particular addresses or into particular pieces of the memory of other processes. That's something that's relatively new, and it is not very frequently used. So I think one-sided communication comes closest to, let's say, something like a partitioned global address space. Like I said before, I don't particularly like that model. It's efficient, but it is still important that you think about what you're doing there. You can't just peek and poke into somebody else's address space, because it's an inherently slow operation. What MPI also has, it has topologies. So topologies means that I can map communicators or particular subsets of communicators onto characteristics of the network. So if I have some computers that are, let's say, physically close together and can communicate faster than others, then that might suggest that I let them do similar jobs that need a lot of communication, and other pieces of my machine that is not as closely coupled do something else. I can do this with topologies. And then MPI in newer incarnations also has the ability to increase the number of processes that participate or to decrease that. More information on all of this you can find on a website that is called the mpiforum.org. That's the place where you would find the standard that defines exactly what every operation does. The standard is a very technical document. It's not something that you would read very frequently unless you already know what you're looking for. So I personally often look into the standard if I need to know, okay, I know I want to call MPI receive, but I have forgotten the order of the arguments. That's something that I can easily find in the standard. The standard, however, is not the place where you want to find out, well, in what circumstances would I use this function versus that function. That's not described in the standard. That's an interpretation, right? The standard only defines what exactly it is that this function does and what the arguments are. Okay, so I would like to end this section with an example where I show you how to compute a matrix vector multiplication. So let's say I have a very large matrix. I assume it's a full matrix for simplicity, n by n. So n might be 1,000,000 or larger. And I want to multiply this matrix by a vector of size n. So I assume the matrix is dense. Let's assume I have p processors, and every processor stores n over p rows of this matrix. Similarly, it's going to store n over p elements of each vector. For simplicity, let me assume that n is a multiple of p. So the way I can define these data structures, here's a little bit of pseudocode in C or C++, and you will forgive me that there's no comments in here. The comments come by voice. So let's say I have a class that is called parallel vector. It knows it's the total size of the vector, so that would be the capital N. And then it stores the first and the one after the end of the elements that are stored locally. So let's say I have 1,000 elements and 10 processors, then processor 0 would store 1,000, 0, and 100, and processor 1 would store 1,000, 100, 200, and so on and so forth. And then it has a pointer to the elements that it locally stores. So that, in the example, would be a pointer to 100 doubles. So when I initialize an object of this kind, I call the constructor with the size and the communicator that goes with it. So with the universe in which I want to work, it sets the size. It asks MPI, what is the size of this communicator? So how many processes participate in this? So in the example I just gave you, that would return 10 in this particular variable. And what is my rank? What is my number within this communicator? So that would return 0 or 1, for example, or let's say 0 to 9. And I store this in these variables com size and com rank, in my rank. With this, I can compute what is the first element and the one after the last that I store, namely that is size divided by the number of processes times my rank and times my rank plus 1. And then I can allocate the corresponding number of elements of this vector. I can do the same thing for a parallel square matrix. Okay, it's going to store the size, which rows of this matrix I store, a pointer to the elements, and it can do exactly the same kind of operation. Here's a graphical representation. So let's say I have this global matrix here, okay, and a vector x, and I want to multiply these two together and write the result into a vector y. So on, let's say this looks like processor 3, for example, the red rows of this matrix are the ones that I store on this particular process. And the red elements are the ones that I store on this particular vector. And the blue ones, they live on other processors, right? Every processor has its own share of rows of this matrix. They don't overlap. Every processor has a disjoint set of pieces of data, and only if I consider them all together do they actually form this matrix. So if I want to multiply a times x on the processor that I'm at, essentially what I need to do is I need to form the dot product between this row, for example here, with the entire vector x, and I need to write it into this element of y. And then I need to do the same thing for the second of the locally stored rows of a times the entire vector x, and I'm going to write it into the second of the locally stored elements of y. So here's a simplistic algorithm that would do this. So you may have to look at this again offline or pause this video if you want to really see every detail. But let me try to run you through this. So what I'm going to do is I'm going to have a loop over all of the block rows, or row blocks. The row blocks are in this picture here. This is my own row block. Let's say there is one for processor 0 from here to here, and another one from here to here, right? So there might be in this picture maybe 6 or 7 row blocks, if that means that 6 or 7 processes participate in the current universe. So I'm going to run through these row blocks, and then if this is my own row block, okay, so if row block equals my rank, then I'm going to run through the columns, the column blocks in this thing. So I can do the same thing again. I can split each one of these row blocks into corresponding column blocks here. Why do I do this? With my own piece of data that I have here in x, I can multiply with the corresponding column block over here. But in order to multiply, let's say, these elements here in my row block, I need to have these elements of the vector, which I don't have locally. So I'm going to run through the call blocks, and if this is the column block that corresponds to my rank, then I can do the product with the data that I have locally. Okay. But if it is a column block that I don't own locally, or let's say where the corresponding data is stored somewhere else. So let's say if I'm in the very first column block here, let's say in this square part of the red zone, I need to multiply with these elements from another processor. So if that happens, I'm in the else here. I'm going to allocate some memory, and then I'm going to call MPI receive, which gets that data from somewhere else, from the processor that has it. and that processor has to send it, of course. But let's say for now I'm only going to receive it. Once I have received it, so once MPI receive comes back, I can do the matrix vector product again, and then I can delete my my buffer. Now I do this for every column block. Okay, so for every column block here and here and here, I ask either do I own the corresponding elements of X locally or not? And if not, then I wait for the data to be sent, and if I own it, then I do the matrix product. The outer loop was over all of the row blocks. Okay, so let's say if we're currently dealing with the first set of rows here, there's nothing for me to do. But I do know that the processor that owns these elements here will need my data. So if I'm in a row block that I don't own, I get into the else block here, and I know that the processor that we're currently dealing with, namely row block, will need my elements, so I'm going to send it to this processor. Okay, so that's the way how we deal with the distributed nature of data. That, well, if I don't have data locally, I need to send it, and the other processor can receive it. There are many things wrong with this implementation. Namely, I only send data the moment when I need it. So the receiving processor typically has to wait for this and has nothing to do in the meantime. A better algorithm would send the data to all of the processors once it's available. That means at the very top of the function, I already know I have all of the data that will ever be necessary to compute this matrix vector product. I might as well send it to everybody who needs it, right? Then I would like to receive it only as necessary. So the general rule is to send data as soon as possible and to receive it as late as possible, and in between do something useful. The other thing in this example that I just showed you is we repeatedly allocate and deallocate memory, and we should do this only once, of course. So here's a better implementation. I'm going to start at the very top. So I'm running through all of the row blocks. And if the row block is mine, then for now there is nothing to do. If the row block belongs to somebody else, I know that that other processor will need the elements that are stored locally, and so I'm going to send them to the other processors. Okay. While the sending is going on, I could use an isend if I wanted here, by the way. So while this is going on, I will do the local piece of the matrix vector product I can do with the data that I have locally. And only when I'm completely done with doing everything I can do with my data, then will I go back to those pieces of the column blocks for which I needed to have data from somewhere else. So I'm going to loop through all of the column blocks of the red zone, and for the ones that I haven't dealt with yet, namely for all of the ones for which the column block is not equal to the number of my own rank, I'm going to wait for the data to come in. Maybe it has already, and once it is there, I will actually do the work. So that's sort of the more efficient way of implementing things. A few notes at the end here. So usually you need data that resides somewhere else. That requires communication that is unavoidable. That's part of MPI. What that means in practice is that with MPI, you always live in that conflict zone between trying to keep as much data locally as you can, so that you don't have to communicate, but at the same time, if you want to keep too much data locally, then eventually you will run out of memory locally and it doesn't work. So you live in this conflict zone of, well, wanting to store as much data as you can locally because it avoids communication, but not wanting to store too much, right? That's always the trade-off. Like I said, MPI makes the flow of information explicit. It forces programmers to design data structures for communication, and that typically leads to efficiency. If you look at most MPI programs, they actually do not have a lot of MPI calls. So from the perspective of somebody who writes this, most of it actually goes on in your mind. You have to think about how these data structures look like, but you don't have to write hundreds of MPI calls. At the very end, there's alternatives to MPI. If you don't like that interface, there is something that is called Boost MPI. It wraps these things. You don't have to say what the data type is. C++ can infer that for you. As I said, there are other languages that have the pros and the cons. I alluded to them. But by and large, I think if you understand how MPI works, you will find it reasonably easy to work with this. So I think with this, I'll leave this introduction, and then we'll come back later in the next lectures and look at concrete examples of how you work with MPI, for example.